So, before we get started, go ahead and take a minute and look at these options A, B, C, and D and let me know, circle them, and tell me which of them are solved for one variable. So, this is language that we would have seen when we were solving literal equations. But go ahead and let me know which ones of these are already solved for one variable. All right, welcome back. So hopefully you notice that A here is solved for one variable. And what I mean by that is that A here has y all on its lonesome right here on the left-hand side, and everything else is on the other side of the equation. So that's what we mean. Something is isolated by itself or solved for. So now we're going to go ahead and solve each of these remaining equations for the easiest to solve for variable. And what I mean by the easiest to solve for variable is sometimes there's a variable that's going to be less work to solve for than the others. Sometimes it's kind of even, it doesn't really matter. Here, if I chose to solve for this x, I'd have to move this y, but then I have to figure out what to do with the 5 here. But if I want to get y by itself instead, all I have to do is get rid of the 5x right here. And so that's what we're going to do. We're going to take this y here. Oh no, I thought I turned my highlighter on. We're going to take this y here, and I want to isolate that y. So let's go ahead. That was a little bit crazy size, huh? That's better. All right, and get this y all on its lonesome by subtracting 5x from both sides. So now I've got y is negative 5x minus 8. So now we would say that this equation is solved for y. Alrighty, let's look at C. Again, here there is a coefficient on x, or a number in front of x, that negative 3. But this y here does not have something out front. It has that invisible coefficient of 1, but of course, that's not something that we can get rid of or need to get rid of. And so to get y all on its lonesome, we're going to add 3x to both sides. Now remember, right, this 12 and this 3x here, those are unlike terms, right? One has variable x and one doesn't, so we can't combine them to get something like 15x, right? They stay separate like this. All right, and one more, let's look at equation D. This is what I was talking about earlier, where notice that x has a coefficient, but so does y. So really, it doesn't matter. This is where normally if we were in person, I would say, hey, what do you want to solve for? But since we do usually solve for y, let's go ahead and do that together. So it's going to be multiple steps, not just one. Here, I'm going to subtract 2x from both sides, and I'll have negative 3y. Don't lose that negative when you rewrite the problem. All right, and now to divide both sides by negative 3. And so if I want this to be written as two separate fractions instead of one fraction, divide everything. So I'll have 2 over 3, since those were both negative, x plus 1/3, like so. And now y has been solved for there. All right, so why are we doing this? Well, the reason that I wanted to get you in the mindset of solving for one of the variables is because that's actually how we're going to go about solving systems today. So today we're talking about our second method of solving systems of equations. The first one, we did graphing. Now we're going to look at solving a system of equations with what's known as substitution. Now, remember, right, I always say in math, we're not creative when we name things, we tell it like it is. So, substitution, right, that's a word that we use, right, in our everyday lives, right? We think about substitutes or subbing somebody in. So, um, it's going to have the same meaning in algebra. So the first thing that we're going to have to do when we're trying to solve a system of equations with substitution is we're going to look at the equations. We got to get the lay of the land. We got to figure out what's going on here. Is one of them already solved for one variable? Because if so, that's great news because that makes our lives so much easier. If not, that's totally okay. We're going to choose the easiest. Oh boy, can't spell. The easiest variable to isolate or get by itself in one of the equations. Not both, just one of them. All right, so once we have a variable solved for, or one equation solved for one variable, right? So an x equals or y equals, we are going to substitute, hence the name, the expression for the solved for variable into the other equation. All right, so once we've substituted that into the other equation, we're going to solve for the remaining variable. Then we're going to substitute the value you just found when we solved that equation into the other equation and solve. That way we found our x and our y value for our ordered pair. Then of course we're going to check our solution in both equations, right? Because we want to leave knowing that we got the right answer. We don't want to be left in the dust. All right, so let's go ahead and do our first example. All right, so that first step, remember, was we were going to look at the equation and see is one of them already solved for one variable. And so if you notice, our top equation here is already solved for y. Okay, so that is excellent news here. It's already solved for y, so I don't need to solve one of these equations for a variable. So what we're going to do, I'm going to call this guy equation 1. Okay, and I'm going to call this guy equation 2. That way it's easy to keep track of them. And we're going to take the right-hand side of equation 1 and plug it into equation 2 in place of y right here. So what I like to do is I'm just going to rewrite equation 2 as negative 3x plus, and then I like to put in parentheses since I'm doing a substitution. And I'm going to take this 2x right here, and it's going right into this function, right? I am substituting that value into this equation. All right, well, now I can start combining my like terms and solving. So if I'm in debt 3 x's and a kind citizen donates 2 x's to me, I'm still in debt, not as much, 1x. So negative x is equal to 12. I can multiply or divide, doesn't matter, both sides by negative 1 to discover that x is going to be negative 12. All right, well now what I need to do is I'm going to bring equation 1 back up here, right? Y was equal to 2, but instead of putting x, I'm going to plug in negative 12, right? The value we just found for x. And when I multiply those 2 times negative 12, I get negative 24. So far, right, the ordered pair that we found was negative 12, negative 24. Alrighty. Well, we gotta check our work here. So, how I'm gonna check my work is I gotta plug this into equation 1 and plug it into equation 2 and see if it ends up being true. So, equation 1, remind you, was y, so in this case, negative 24. And we want to know, is that equal to 2 times negative 12? Since that's the equation we just used, hopefully we didn't mess it up too bad, right? Negative 24 is negative 24. We are good to go there. Alrighty. Now over here, if we're plugging into equation 2, wow, I did not leave myself a whole lot of space here, did I? Alright, let's scoot that over a little bit. Alright, that's better. Okay, so now equation 2, like 3x plus y equals 12. But remember, we put this question mark over the 12 because we're like, I hope it's equal to 12, but I don't know. That's why we're checking. This was negative 12, our x value, and this was negative 24, our y value. All right, and so 3 times negative 12, that's going to be negative 36. Oh boy, we almost messed up here, y'all. I wrote my equation incorrect, so that's going to be positive 36 right there. Times my little scribble erase doesn't work. Alright. That's what I get for zooming in like this. I hid my negative from myself. Alright, so 36 minus 24. And of course that is going to be 12. Is 12. So awesome there. So now we can box up our answer here. You know, it is correct. Next. All right, look, only a couple more examples, guys. We're making good time. All right, so here we've got example 2. We're going to solve a substitution. Now, when I look at this, none of these has a variable that is solved for. And unfortunately, they all look kind of like they'll be a little bit similar. I think I'm going to end up choosing let's solve for this x here, because when we get rid of that negative, we won't have to deal with any fractions. But if we divided by any of those coefficients on the other variables, we'd have some fractions. All right, so what we're going to do here, again, I like to kind of start out labeling my equations. So we'll call this guy 1 and we'll call this guy 2, so I know what I'm talking about. And we're going to solve equation 2 here. We're going to isolate x. So we have negative x plus 4y equals negative 1. All right. So let's start by, we have to subtract 4y to both sides because we have to get rid of any addition or subtraction before we worry about the multiplication or division. So we've got negative 4y minus 1. Now we can, this time we're going to multiply both sides by negative 1 because I divided last time and we just want to, spread the love. So we're going to end up with x is equal to 4y plus 1. All right, so this is our new equation 2. It's the same value, just looks a little bit different as our first equation. So what we're going to do is we're going to plug that in. So where we used to have x in this top equation, we are going to put this whole thing, this whole expression, 4y plus 1 is going to go right in here for x in this equation. So when I go to rewrite it up here, I'm going to write 2. I'm going to leave a nice big space with my parentheses so I can fit that binomial. Minus 3y equals minus 3. Oh, silly me. That was supposed to be green. Gotta keep my color coding in check here. Alright, so now I'm going to plug in my 4y plus 1. First thing we gotta do is distribute. So now I'm going to have 8y plus 2 minus 3y is equal to minus 3. We'll have 5y after we combine like terms plus 2 equals negative 3. Subtract 2 from both sides. 5y is negative 5. Divide everything by 5. We'll get y is negative 1. Alright, well this is stellar news because now we can go ahead and take this y equals 1 and we're going to plug it in to our already solved for equation, right? So we can use this guy right here because it will just spit out x for us. So x is 4 times this negative 1 we just found plus 1. So that means x is negative 4 plus 1, or x is negative 3. Alright, well now we gotta check our work. So if I check them in equation 1, it's gonna look like 2 times negative 3 minus 3 times negative 1 hopefully equals negative 3. And then equation 2, that'll look like negative times negative 3 plus 4 times negative 1 hopefully equals negative 1. Alright, so here what happens, it's going to put negative 6 plus 3, which is going to be negative 3. So that's good. This will be positive 3. This will be positive 3 minus 4, which is going to be negative 1. So that works as well. So you're going to want to check with your algebra teacher about this, but I personally don't mind if you box your x and y separately, like this. But your algebra teacher might request that you always write your answer as an ordered pair. So just make sure, I'm personally fine with this, make sure you know what your algebra teacher is looking for. Alrighty, example 3. Alright, let's go ahead and do this one on our own. So go ahead and pause the video right now. Actually pause it and do this one yourself, and then we'll come back. Alrighty folks, welcome back. We are going to solve example 3. Now remember, you may have decided to solve this equation or the system differently than I did, but as long as we end up with the same answer, that's a-okay. As long as everyone's doing their work correctly, then it's totally fine to do it a different way. So for example, I'm looking at this and I noticed the easiest to solve for variable is going to be x in the bottom equation. However, maybe you didn't notice that, or maybe you like a challenge and you decided to solve for a different variable. That's okay. We could still end up with the same answer. Again here, solving for x in equation 2. It's funny, that's what we just did. And the last one, but a while. Alright, I'm going to start by adding 2y to both sides. I'll get that x is 2y. Alright, so x here is 2y plus 3. Alright, so now that I have x solved for, I can substitute that in for x in equation 1. So, equation 1 looks like 3 times, used to be x, but now it can be something else, plus 2y is 5. And here we have 2y plus 3. Alright, now we can start to distribute. So we have 6y plus 9. Don't forget to distribute to both of the terms in the parentheses. And combine our like terms. Then if you're like me and you start running out of space, I like to just draw an arrow here so that I can keep all my work organized. And when I look back on it, or somebody else is looking back on my notes, they aren't scrambling to figure out what's going on. So here I subtracted 9 from both sides. I'll divide both sides by 8. And this is going to be negative 1/2. All right, well, I'm gonna work smarter, not harder, and I'm gonna plug, whoopsies, I'm gonna plug this 1/2, this negative 1/2, in for y, not there. I mean, I could, but I have to do more work. If I plug it in here, though, it'll just pop out x, which is so nice. So we'll have x is 2 times negative 1/2 plus 3. Well, that means x is, those 2's will cancel. It must be negative 1 plus 3. Or x must be 2. Okay, so if I'm writing this as an ordered pair, again, that's going to be 2 comma negative 1/2. Not boxing it up yet, right? Because I got to figure out what's going on here. Is this correct? We got to check our work. So I check it in equation 1. What's that going to be? I'm going to check it in equation 2. Alright, so again, we're plugging in 2 where there was an x and negative 1/2 where there was a y. So this looks like 6 minus 1, and that is 5. So good news there. This looks like 2 plus 1, and that is 3. So great news there as well. All right, hopefully y'all have made it this far with me. Let's go ahead and solve this last one here using substitution. So good news with this one, guys. Something's already solved for. So y here is already solved for. So I don't have to do that. I can jump straight to substituting, right? So what I'm going to do is I'm going to take where this y is here, I'm going to replace it with this expression that we know is equivalent with y. So we're going to have 6x plus 3 times, and you're totally allowed to do substitution, by the way, right? Because we said y is negative 2x plus 4. Like, those are the same thing. They're equivalent, which means that they are interchangeable. And we're using that fact to our advantage. All right, now I'm going to distribute 6x minus 6x plus 12 equals 12. We combine our like terms and whoop, those cancel. Get 12 is equal to 12. Huh. All right, so what this is 12 equals 12. And hopefully you agree with that. This is what's known as a true statement. And notice I don't have any variables left, right? There's no x's left in my equation, there's no y's. So what happened here is that these guys are what's, so what happened is no matter what I plug in for x or for x and y, well, it does matter, but there's going to be an infinite number of points. This is what it means. There's going to be an infinite number of points that I can plug in to make this true, right? Because 12 equals 12 is a true statement. So when I had taken x out here, there's nothing I could plug in for x that would make this equation untrue, right? 12 is always going to be equal to 12. So this is infinitely many solutions. And this is the algebraic side of what we saw graphically the other day in our solving by graphing video, where these look like, so if I were to draw a little sketchy sketch here, I was trying to think, -2 up 4, -2 slope would look kind of like this, right? So this is my equation 1. Equation 2 is really the same line. It would like graph on top of it. They're what's known as coinciding lines. So that means instead of having one point in common, they have all of their points in common because really they're the same line. So actually, if I solved 6x plus 3y equals 12 for y, it would simplify down to being the same thing as y equals -2x plus 4. It's just a multiple, right? We rearranged it so it looks a little bit different. So it is totally possible in solving by other means, not just graphing, to end up with a situation here where I noticed these guys are infinitely many solutions. Now, if I had gotten a false statement, so here, let's not, well, hold on. Let's add like a ruled page here. So if I had gotten a false statement, so say I was solving and I got something like 12 is equal to 45. Well, that's not true. And so that would mean kind of the opposite, right? So that would mean no matter what I plug in for x, I'm not going to make that true. And so those would be, those lines would be parallel and they would have no solution. And if you remember, right, parallel lines are running together like so, and so they never intersect. All right, everyone, look at us. 2 methods down, 1 to go. Make sure you stop by and learn with us how to solve systems by elimination next.